We go now to the second paper. It's called Impact of Inverter-Based Generation on Island Detection Schemes in Distribution Networks. It will be presented by Mr. Demetris Chrysostomou. He is a master student in robotics systems and control at ETH Zurich with electrical engineering degree from the University of Cyprus. Previous work includes a technical report on assessment of the loss of mains anti-island protection for the Cyprus distribution systems and a journal short-term electromagnetic interference on a buried gas pipeline caused by critical faults events of a wind park, a realist case study that was presented on IEEE industry application. Mr. Chrysostomou, you have the floor.
Thank you very much, and hello to everyone. Let me first share my screen. Yes. Are you available to see my screen?
Yep.
Great. So first, yeah, I'm Demetris Chrysostomou, and this is a presentation for our approximation of the non-detection zone on distribution grids. So our problem overview is that we focused our research on unintentional islanding, since we noticed that owing to the increase of distributed generation in current power systems, the risk of unintentional islanding is very important. And we also realized that there are advancements in power systems that make some traditionally used protection schemes become obsolete. So in order to study those traditionally used protection schemes and find their significance in current power systems, we use the notion of non-detection zone, which defines the set of disturbances that will not trigger the system protection. So the model we created for our simulations followed international standards, and it's split in two different time zones: before the loss of main event and after the loss of main event. As we can see, the load used in such models is RLC, since it is the worst case scenario. And the most important components that will play a significant role for the after the disconnection is the grid powers that are given or obtained from the distributed generation and the load, delta P and delta Q. Those powers after the disconnection will be lost and will cause the voltage and the frequency of the system to change. So first, we'll start with the non-detection zone computation and the traditional or current approximation that exists. So for the analytical approximation of the non-detection zone, we are trying to find these relationships that are delta P over P and delta Q over P, and show for which delta P and delta Q, the voltage and the frequency after the loss of mains event will not trigger the protection. However, the existing approximations have some drawbacks. One of them is that they only focused on the grid feeding mode and not in some other modes that are used more and more over the years. And another issue is that they oversimplify their analysis, so they ignored dependencies between voltage and reactive power, as well as frequency and active power in their relationships, and therefore the non-detection zone that they are predicting has this square rectangular form. So the way they used to define and to derive those relationships is first by bearing in mind that the power before and after the disconnection of the load and the grid and the distributed generation, the power after the disconnection, becomes the same for both of them, since the grid was lost. Another assumption is that the distributed generation power remains the same before and after the event, since we are in grid feeding mode, and therefore the change or the change on voltage and frequency comes from the load components that need to change their powers to reach the disciplinary generation ones. Therefore, applying this information, we can express some relationships delta P over P and delta Q over P as shown previously. So first, for the delta P over P case, the result that is currently obtained has this form, which is only related to the voltage after the disconnection, and the reactive power is not present in this relationship. Therefore, then they represent this voltage after the disconnection with the voltage limits and obtain the cases where delta P over P will not trigger the voltage. And since delta Q is not related, we can see that this voltage limit, the protection is not affected by this delta Q dimension. Similarly, for the delta Q with frequency case, there is no delta P dependency, and the lines we are obtaining are horizontal and parallel to the delta P, since delta P is occurring not to affect the frequency. Therefore, after studying the current approximation, we improved it through introducing dependencies between active power and frequency, reactive power and voltage that changed the shape of the non-detection zone. But we also improved the accuracy of the grid fitting mode since we introduced those dependencies, and we took into consideration more compelling converter control schemes. Then we validated our analytical approximations through EMT simulations. So for our improved EMT simulation, the operating modes that we also introduced is the grid forming and the grid following, where grid forming can be expressed as ideal voltage source and grid following as an ideal current source. Grid following can be then split again into different subcategories: the grid fitting that already has a non-detection zone approximation, and the grid supporting, which changes the voltage and frequency on the terminals of the generation according to the measured active and reactive power changes. Therefore, applying the Drup equations, we can use them to obtain the non-detection zone. The process we followed for to derive the approximations is first by starting with the grid supporting mode, deriving the non-detection zone for that, and then simplifying it by setting the Drup constant values to 0 to obtain the grid fitting mode relationships, and also flipping the Drup constant values to obtain the grid forming one. Therefore, following the same process, we start with the grid supporting approximation. First, we apply the Drup control law, and we are obtaining delta P over P and delta Q over P relationships that, however, are not in the form that is desired, since they have frequency and voltage dependency present in same equation, same relationships. Therefore, to remove those frequency from the delta P over P relationship and voltage from the delta Q over P relationship, we needed to derive new expressions. Those new expressions derived as shown here. However, they still have one issue, that they have the RLC load parameters. RLC load, although is a constant value, in loss of main studies is what we change in small steps to obtain the non-detection zone. Therefore, is not constant in this case. And to obtain constant values, we found relationships that represent this RLC load with the resonant frequency components L0, C0, and R0. Finally, the result can be shown here, which for simplification purposes, we defined also some of our own variables because the appearance is rather complex. Then for the grid fitting case, we just set the Drup constant values to 0. And then we were able to compare it with the traditional approximation, where we realized that delta P over P had the correct form, but delta Q over P, in our case, introduced this dependency between active power and frequency, which is linear, and we shape the non-detection zone to a rather trapezoidal one. Finally, for the grid forming case, as said previously, just by flipping the Drups, we're obtaining the final approximations that will be obtained following the whole process from the beginning. And now we're able to test and validate our results. To validate our results, we created a system that is consisted by the distributed generation, the load, the grid, and the circuit breaker, plus some additional other components. And the protection settings that we used followed British standards. The system setup, this is here a generic structure of control scheme combining the system level control, device level control, and device model. And after using that system, we were able to obtain the final the simulations that will give us a non-detection zone and compare it with the traditional approximation and our approximation. So first, starting with the grid fitting mode, we can see that traditionally it had this bare form. Through our improved approximation, we obtained this trapezoidal form. And then through the simulations that are presented with the circles in the graph, we have perfect matching between our approximation and the simulations. After that, we wanted to test the grid supporting case, which has the only difference that in this case, droops have values. So in this case, again, the simulations and the analytical approximation we have perfect matching, and therefore we're able to validate our results and make some conclusions about the effect of the droop that is added in the grid supporting case. So the conclusions we had about the effect of droops is that as droops are increasing in the grid supporting case, the non-detection zone is increasing dramatically, and it might become ineffective since it will fail to for a great amount of cases to recognize islanded operation. After that, we tried to validate the grid forming case, and for that we first noticed that the non-detection zone for normal droops had extremely high values, as can be seen in this graph, and therefore it was hard to validate using our simulation model for normal droops. For that reason, we increased the droops of the model to abnormal values, and we increased the droops to our analytical approximation to abnormal values as well, and we're able to obtain the simulated and the analytical non-detection zone, which has some the matching is quite good, but has some differences owing to discretization steps and the effect of the system working in abnormal cases. So the conclusions for our research is that first, there are several problems with existing non-detection zone approximations. We improved the non-detection zone estimation for grid fitting case. We also introduced our own formulation for grid supporting and grid forming, and we validated our results through EMT simulations. Thank you very much. Do you have any questions?
Thank you for a very timely presentation. And let's see if we have some questions on the Q&A. Well, people are feeling shy this afternoon, I guess. So I have one question. Could you go to your slide, I guess, 10? The one that you have the system with the EMT.
This?
No, yes, that one. How did you simulate the transformer? Did you include saturations and also how do you simulate the line model? Because they could affect the whole performance of the system if this, I mean, if the saturation is included, and then if you have a long transmission line, it could also add some delays.
Yes, so in our protection settings, we simulated some, we added some additional delay of a small amount of milliseconds. However, we followed the standard settings that in this case, the lines are considered to be ideal without losses, since the main components are the load and the distributed generation, as well as the grid and the circuit breaking.
Okay, and what about the transformer? Did you include saturation in the process, or it's just a simple transformer?
Yes, it was just a simple transformer. Yes.
Okay, okay. Thank you. Very interesting work. So let's see. Then